Good morning, everybody. Welcome to Advanced Electrical Networks. This is lecture 25. So today we will start learning about time varying circuits and systems, and like everything else, we will concentrate on linear time varying circuits and systems, right. So, before we get into the details, I'd like to address the first question you might have in your mind, namely, why should I learn about, or why should I even care about time varying circuits? And the answer is not far to come by. Well, if you look into your pockets, your cell phones are basically radios plus a whole lot of extras added. And if you go back in time, to motivate the need for time varying circuits, if you go back in time and looked at say a radio maybe 100 years ago, remember, and this is what it would look like. The RF spectrum basically is, as you are probably aware, consists of many signals, right. So, it is a crowded space, and what you are interested in is perhaps a small desired signal. And along with the small desired signal, there is a whole lot of large unintended interferers. And many of these large unintended interferers can be 5 or 10 orders of magnitude larger than the small desired signal. So, the job of the radio is to basically somehow get at the small desired signal from this mess of signals, which are several orders of magnitude larger, right. And you need to eliminate all those large signals, and then somehow pick out this small signal and amplify it to a level that will be eventually you will be able to hear it with the human ear. Now, the question is, the first question that comes to mind is, why don't I simply amplify the signal? Well, we need this chap. So, why don't I simply amplify the signal right away? Well, you have a small desired signal, but there is a whole lot of undesired stuff which is very large compared to what you desire. And if you amplify the whole signal as is, then your amplifier is going to saturate, because the interferers are going to saturate the amplifier, correct? So, it does not make sense to amplify the RF signal as is. What do you need to do therefore? Well, you attempt to eliminate the interferers, right, and amplify. Once you eliminate, once the interferers are reduced in amplitude, you can amplify a little bit. Then you can go and reduce the interferers a little more by further filtering and further amplification, and so on and so forth. So, that was the among the first ideas that was attempted to realize a radio, right. So, you have a band pass filter, okay, and remember, these filters have to be extremely narrow, all right. And as you have already seen in your assignments, making a very high quality factor narrowband filter has a lot of implications with respect to noise, right. So, therefore, you want to make a high order band pass filter. It does not make sense to put the entire band pass filter right up front, okay, and then amplify the result. And the reason is that, as you have already seen, if you cascade a whole bunch of, somehow make a very high order band pass filter, you lose a lot of signal, right. And the moment you lose signal, it is equivalent to taking a hit in the noise factor. So, what you want to do is, do some coarse bandpass filtering, then you gain up the result to however large you can without saturating the amplifier. Then now the signal here has got, it's got the small desired, slightly amplified desired signal, but more importantly, the difference between the interferers and the desired signal becomes smaller as a consequence of the bandpass filter upfront. Does it make sense? All right. And then, you need to get rid of the interferers further. So, you put another bandpass filter, some more gain, and then you do this until, let's say you have 10 stages of this. What will happen eventually? Well, the equivalent transfer function is that of cascading a whole bunch of narrowband filters, and you know that if you have a filter like this and you cascade one more like this, you basically will get a result which is narrower, right? So, when you cascade a whole bunch of bandpass filters and amplify them up, so as far as the transfer function is concerned, from here to here, you have a lot of gain and a very high order bandpass filter, right? And the hope is that at the end of this RF receiver chain, you basically end up with only the desired signal. And then once you have the desired signal only, you can detect its envelope, for instance, by using some kind of nonlinear detector. A common thing to do those days was to use a diode. I'm sure all of you have seen this. Right, this is basically an envelope detector, right? So once you detect the envelope, it's like you have the baseband signal here, and then you go into an audio power amplifier. So this is all RF, and this is all baseband, and you go into an audio power amplifier, and then which drives the speaker, right? Now there were several nagging problems with this radio receiver. This is what was called the tuned RF receiver, and there must have been some problems with this, which motivated the search for better ways of accomplishing the same task, right? What do you think the problems posed by this way of receiving a radio signal are? What all do you think might be problematic? Okay, so one problem is that all these bandpass filters better have their center frequencies lined up to the exact same value. It doesn't help if one filter is centered at f0 and the neighbor is centered here. So if you do that, then you basically have when you put 10 of these such things together, you basically are not receiving anything at all, right? So these were all made with inductors and capacitors, and therefore you needed to make them very, very carefully, so that when you made 10 of them or 15 of them, right, the center frequencies of those would be ideally, of course, would all be identical. In practice, because of mechanical tolerances, it's not possible. The moment you do that, there is the cost goes up, and not only that, you may tune them in the factory, but when you bring the radio set home, the center frequencies have drifted. So you would basically need to have some minor adjustment of each of these. You'd have to bring the radio home and then carefully adjust some screws on each of those bandpass filters, so that the station you hear is very loud, right? That brings us to the next problem. So this is, of course, problem 1 is center frequencies need to be aligned. Okay, what could be the next problem? Pardon? I can't hear you. Yes. Okay, well, it stands to reason that you're buying a radio to be able to listen to a whole bunch of stations, right? So, if you want to listen to a different station, what should you do? Well, you need to move or tune the band pass filter to the next station, and again you must make sure that not only are these aligned for one station, the center frequencies must be aligned for all stations of interest. So, in other words, basically you have all these must be, what do you call, ganged together, so that when you go and turn one knob, the center frequencies of all these band pass filters move exactly the same amount, right? I mean, it's hard enough to keep the center frequency identical even if you didn't have to tune the band pass filters. Now, over the entire AM range, for instance, which is a factor of 2 to 1, right? You basically, or more, you basically are now reduced to you now have the bigger problem of being able not only matching these center frequencies, but being able to tune them over a wide range while still matching the center frequencies. Okay, so this ganging, right? Again, as you can see, is all these are in principle doable, right? But in practice, when you have to machine these components, and there are finite tolerances, and to keep these tracking over temperature and so on is a real challenge. Okay, what next might be the problem? Pardon? You need? Oh, well, I mean, if you want low noise, well, you need inductors and for the band pass filters, and yeah, fine. Okay, what comment can you make about if you want a narrowband filter, the quality factor of each of these inductors and capacitors must be, or the quality factor of that parallel RLC circuit must be some large value. Now, if you tune the center frequency and the quality factor remains the same, what comment can you make about the bandwidth? Let's say the center frequency in radians per second is omega naught and the quality factor is Q. What is the bandwidth? Omega naught by Q, correct? Now, if you let us say your omega naught changes, you're changing from one station to another, let us say your omega naught changes by 20%, right? What comment can you make about the bandwidth? Pardon? Well, the third problem is that the bandwidth changes with the center frequency, right? Because Q is largely constant across frequencies. Fine. Any other problem that you can think of? Pardon? Well, that's happening here, right? I mean, the demodulation is happening at when you detect the envelope. Well, in those days, people weren't too worried about spectral efficiency, so you could get away with nonlinear demodulation techniques like this. This is not optimal spectrally, but that was okay in those days, right? Of course, now you have an A to D converter, and then whole thing is done electronically. So you because bandwidth is very expensive, and you want to make sure you want to do whatever it takes to save bandwidth. But it's not a fundamental problem, right? So the next problem, or a very important problem of this structure is the following. What comment can you, as we already have seen, what comment can you make about the gain of that entire RF chain? I mean, is it very small or very large? Right. Finally, when you go from here to here, at the center frequency, you find that the gain must be large enough to push this by several orders of magnitude. So it's not uncommon to have a gain of 10 power 5 or 10 power 6 from the antenna to the output here, all right. And on top of that, you have a cascade of, you not only have gain, but you have a cascade of filters. So you have in effect a high gain system with a very, very high order. If you have, I don't know, if you have 6 filter stages, each stage is second order at least. If you assume that the gains are, have no frequency dependence, and if you put 6 of these together, you have a 12th order system with a very, very large gain. So what? No, the reflection from the speaker is at what frequency? So you have a high order. What about stability? Yeah. So stability only, as far as I can remember, is only the problem when there is feedback, right? Yes, any other thoughts? I mean, what issues? Yes, Devin, you were saying something. Well, okay, fine. I mean, linearity is, yeah, okay, you got to make, the amplifiers linear. That's, you have a high gain and a high order system. So, what should you be worried about? I mean, somebody says stability, which is a step in the right direction, but, when I last checked, stability is only a problem when you have a feedback loop, right? So, why do you think it could be a problem here? Any 2 points in space have only so much isolation, correct? So, whenever you build something, there is always going to be some spurious feedback path, okay, alright, from everywhere to everywhere practically, right. Now, these spurious feedback paths will basically have, transmissions which can be made very small by careful design, but, cannot be made zero, right. If the amplifier's gain is sufficiently small, then the fact that you have a spurious feedback of, say, magnitude of, say, 10 power minus 6, which admittedly is a very, very small amount of feedback. If you have only a gain of 100 and you have a feedback factor of, say, 10 power minus 6, the loop gain magnitude is how much? If you have a gain of 100 and, and a feedback factor of 10 power minus 6, what comment can you make about the loop gain? 10 power minus 4, so whatever the phase does, the closed loop system will never become unstable. I mean, all of you agree that now, because of the spurious feedback, you have a feedback system, correct? The forward amplifier's gain, unfortunately, in this case has to be very large, of the order of, say, 10 power 6, 10 power 7, right? So, what is your estimate of how much feedback you can tolerate before the system starts to oscillate? Yeah, and what is the gain and what is 1 by the gain? So, if your gain is 10 power 6, then, and you have a high order transfer function in the forward path, then you can tolerate roughly 10 power minus 6 as the feedback path gain before the system starts to oscillate or become unstable. Does it make sense? Right? Because, remember that you want to avoid this, the magnitude of the loop gain becoming 1, right? Because you have a high order system, it's very easy to get that 180-degree phase shift between the input and output, right? So, therefore, a problem with this high gain, this is, therefore, as you can imagine, this signal chain gives high gain at high frequency, alright, and at high frequency is particularly difficult to get isolation, right. As frequency becomes higher, right, parasitic capacitance between two nodes, the impedance of that parasitic capacitance becomes smaller, right. What do you call, the voltage induced in an inductor due to parasitic feedback is dependent on di by dt, and if at high frequency di by dt is larger, and therefore, in general, isolation between two ports can always be expected to degrade with frequency, right. So, the tuned RF receiver, which was early, which was very popular in early attempts to making a radio, had all these problems. So, you would find that you'd first have to bring the radio home and tune each one of these band pass filters until they all were in sync, and then sometimes when you tuned across the frequency range, the center frequencies would go out of sync, and then you have to retune them again. The designer of the radio had to be extremely careful to avoid, or minimize spurious feedback, right? As you know, these small spurious paths is not merely a function of the components, but also the enclosure in which it's put, and whole lot of very, very careful design had to be done. And it was always kind of an art to basically be able to make this radio work, right, in the presence of all these effects. And going to a higher frequency was even more problematic, simply because all these spurious feedback becomes an even bigger problem at higher frequency, right. So, these were all the challenges of what was called the tuned RF radio or tuned RF receiver, and the key aspect of this whole receiver is the fact that up to here the receiver tries to be what kind of system? It tries to be linear. Well, now that depends on how good you make your amplifiers. It tries to be linear, and can you comment on whether it's time invariant or time variant? It is time invariant. All right. Now let's fast forward to modern times.